This is part 2 of the introduction to convergence. We had just left off in the previous video talking about the nth term test, and we had gone through these 4 series. So we're going to actually finally get some insight on what exactly is going on with 1 over n and 1 over n squared. We already know they could converge by the nth term test. Let's finally see if they actually converge. So let's take the whole hog version of 1 over n. Let's take the series version with our generator, and let's write it out here. And if you look at these numbers, what we're going to do is we're actually going to use the integral and Riemann sums to get this list of numbers another way. So let's take this series and write it as an integral. And instead of going from 1 to infinity with n, let's let the integral run from 1 all the way to infinity. And let's take the generator and write it as a function, meaning we need a dx at the end. If I were to take the function 1 over x, pause the video for a second maybe to actually draw this because we're going to be doing Riemann sums in just a second. So if I were to draw 1 over x, and if I were going to approximate this improper integral, it's improper because it goes to infinity. If I were going to estimate it with improper integrals, with Riemann sums, and I wanted to get this specific list of numbers, well, I could definitely do that. Let's set up our Riemann sums here. Now you might be thinking, all right, do I use my left, my middle, or my right? Well, in order to get my first one to be a 1, if I did that, I would have height times base, 1 times 1. That works. Then at 2, then I would plug in 2, and I'd get 1 over 2. 1 over 2 times width of 1 is a half. Then plug in 3. 1/3 times 1 is a third. If you kept going in this manner, you would get this exact list of numbers. One thing you should realize is that our series, which is 1 plus a half plus a third plus a fourth, represents the Riemann sum here. Okay? And our actual integral represents, I'll do the integral in green. The integral itself is the exact area under the curve, which is this right here. So let's find out what's going on with our integral. And maybe if we know what's going on with the integral, we'll know what's going on with the actual series itself. One big thing to keep in mind here is that whenever we do a left sum, our left sum is larger than the actual integral. Because remember, the integral is the exact area. And because all the Riemann sums are adding just a little bit more area, then this list of numbers is bigger than this. This is the exact area in green. This is the Riemann sum in blue. It's very important to keep in mind. Okay, so let's actually go ahead and do our improper integral. This is a really good review of improper integrals. So I can't actually have an integral that goes to infinity. So I'm going to use b. I typically always use that. So I go from 1 to b of 1 over x dx. All right, so what is the antiderivative of 1 over x? ln. So I'm going to do the limit as b goes to infinity of natural log of x. And I'm going from 1 to b. So I'm still writing my limit here. I can't get rid of the limit. The limit as b goes to infinity of natural log of b minus natural log of 1. Well, natural log of 1 is 0. So now you want to think, okay, if I were to plug infinity in, natural log of infinity, let's picture a natural log graph. Natural log slowly grows, but if you went out far enough, our graph would eventually keep going and going and going. It never levels off. So that means this integral is infinity, meaning the integral diverges. So stay with me here. If the integral, which is the green area under here, if this itself diverges, meaning it doesn't eventually go to 0, and my series, which is bigger than that, there's no way that the series, which is bigger than something that diverges, there's no way it could converge. That means the series also has to diverge. Even though 1 over n passed the nth term test, the terms do go to 0, they do not go to 0 fast enough. So the terms do not go to 0 fast enough. It was a candidate for convergence, but because our series is bigger than a divergent integral, our series also has to diverge. So that is how you can use improper integrals and Riemann sums to prove why 1 over n diverges. Now here's another important thing to know about 1 over n. It actually has its own special name. So n equals 1 to infinity 1 over n. This is called the harmonic series. This is one that you need to know by name. A harmonic series is when you just have 1 over n to the first power. And a harmonic series always diverges. And a visual above, this is a quick proof. There's a more formal way to write the proof, obviously, but there's no need to go crazy with it. That is why it diverges. Now, the integral test does not just apply to 1 over n. You can apply it to many different kind of series. So here's how it works. If an integral diverges to infinity, just like this one did here, then the Riemann sum, which is the series, must also diverge to greater than infinity, since the series is greater than the integral. So basically, if you're going to do the integral test, you're going to take your generator and you're going to write it like a function. And then what you're going to do is you're going to actually do out the improper integral. And if the improper integral diverges, then the series also diverges. Let's go ahead and let's move on from the 1 over n, which we just showed converges. Make sure you wrote all that down. And let's move on to 1 over n squared. So we already know by the nth term test that this series could converge because the terms do go to 0. So what we're going to do is we're going to take our generator and our series and we're going to write it as an integral with a function. So we're going to go back to x because it's a function, not really a series or generator anymore. And whenever we wrote this all out, these were the terms we got. Now what we're going to want to do is picture 1 over x squared, which is pretty much the same thing as 1 over x. It just decreases quicker. My picture really doesn't show that, but it does decrease at a quicker rate. And what we're going to want to do is do Riemann sums with it again. And for the purpose of our proof, instead of doing a left Riemann sum, let's do a right Riemann sum. And the reason that we're going to end up doing a right Riemann sum is because we want our rectangles to lie beneath the curve. And you'll see why in a second here. So let's just make sure that this actually makes sense. If I'm at 1 and I plug 1 in here, the height is 1, and 1 times a base of 1 is 1. Then let's plug in 2. 1 over 2 squared is 1/4 times a base of 1 is 1/4. And then let's plug in 3. That'd be 1 over 9 times a base of 1 is 1/9. Oh, good. I am actually getting my series. So this Riemann sum representation here does represent the series. So the series is the same as the rectangle here. And the reason I set it up here, again, is because I want the integral, which is the exact area under the curve. I want our series to be below the integral. So whatever the value of this is, I want this to be less than it. Because again, our Riemann sums are below it. These two represent the same thing. Let's go ahead and actually do our improper integral. So watch carefully here because there is going to be a difference. I'm going to do a limit. Oops, let's do a limit first. I'm going to do a limit because it's an improper integral again as b goes to infinity. 1 to b. And let's write it as x to the negative 2. And let's see here. If I apply my antiderivative rule to it, then that would be x to the negative 1 over negative 1. And I'm going to go from 1 to b. That means I'm going to be doing the limit as b goes to infinity of negative 1 over x from 1 to b. I like to write it without a negative exponent because it's a little bit easier to see what's going to be happening. So I'm at negative 1 over b minus, and I have minus a negative 1 over 1, which is really plus 1. Let's think about what would happen if I actually evaluated this limit now. So I'm going to plug infinity into here. Negative 1 over infinity is going to be 0. It's essentially the same thing. And then 0 plus 1 is 1. This means my integral converges. And if my integral converges, that means this is a finite area, then the series, which is less than the actual area, also has to converge. If you are smaller than something that's converging, you also have to converge. So that is how we can prove that this one, not only did it go to 0, but it went to 0 fast enough. So right here, this is what you want to write. Here is your integral test. So if the integral converges, then the Riemann sums, which again are the series, must also converge because the series was less than the integral. And keep in mind, every series can be written as an integral, and you could apply the integral test to any series, but we'll figure out when it's more strategic to do it. So here is the third test. You did geometric, you did nth term. Now here's your integral test. The integral test is the following. If you have the function and a series, they're going to behave the same. So if you take your generator and write it as a function, just like we did right here, instead of 1 over n squared, 1 over x squared, then the integral, if it converges, then the series will also converge. If the integral diverges, the series will also diverge. So make sure you get that written down. This is very important here. I'm going to look a little bit more in depth at this. Real quick, I want you to add something. For the test that you just wrote down for the integral test, can you please add that in order to use this, the function must be continuous, positive, and decreasing. That is to use the integral test. So please add this on to where you wrote your integral test. So what I did is I rewrote just the basic summary of what happened. Here's my series. Here's how I wrote them as integrals, and here were my results. I want you to think real closely about why exactly did this integral diverge and this integral converge. Right here, when I did an antiderivative, I ended up with natural log. Here, when I did an antiderivative, I ended up with negative 1 over x. And the fact that I'm dividing by infinity and going to 0, that made the difference. Let's think about, because we want to be able to make a general rule here, remember. I'm building up to another test. What if I had like 1 over n cubed and I wanted to do a test? Let's do the integral test on it. So that'd be 1 over x cubed dx. Now x cubed looks really, 1 over x cubed looks really similar to 1 over x squared. It just goes even faster, dipping down like that. Okay, so that would be the limit as b goes to infinity. That's x to the negative 3, so negative 3, x to the negative 2. And then that'd be the limit as b goes to infinity of this here. And whenever I were to plug in infinity here, once again, infinity is in the denominator, meaning this term goes to 0, so I'm left with 3. This also converges. So this is convergent. This is divergent. Okay, let's think about another one here. So first I went from n squared to n cubed. What if I had this series? 1 over n to the half. Here was 1. 1 didn't work. 2 converged. 3 converged. Let's try a half. And think really carefully about what's going on here. It's the limit as b goes to infinity of 1 over x to the half dx. So that's the limit as b goes to infinity, 1 to b of x to the negative 1 half. And 1 over x to the half looks similar, but it's going to not decrease as quickly. It'll have the same general shape, though. Let's do an antiderivative. When you antiderive this, it's 2x to the half. So just like here, after you do an antiderivative, x was not in the denominator. X is to the 1 half. Whereas here, when you did an antiderivative, x ended up in the denominator. So let's continue here. I have x to the half. If I actually plug in b here, the square root of infinity, if I keep plugging in bigger and bigger in things here and doing the square root of them, that's going to be infinity, meaning this one diverges. I want you to think in your head, can I make a general rule about 1 over n to some power for when the series would converge and when the series would diverge? Like if I had 1 over n to the 1/3, would that converge or diverge? 1 over n to the 8th, would that converge or diverge? Or like 1 over n to the 11th. And if you sit there and think about it and look at the examples we did, hopefully you would come up with the following, that if you have the sum of 1 over n to some number, and what mathematicians decided to use was p, it's called a p series. I have the formal rule in a second. If p equals 1, then that would be 1 over n, and that's harmonic, and we know that harmonic diverges. If p is greater than 1, like 2 or 3 or 11, then it's going to converge. The series converges. If p is less than 1, like a half or a third or an eighth, the series will diverge because, again, when you do the antiderivative, x wouldn't end up in the denominator. So I'm going to go back here, and here is your p series test. Oops. And again, it's in the form n to the p power. That's why it's called the p series test. Here's a fourth one that you know. If p is greater than 1, the series converges. If p is less than or equal to 1, the series diverges. You're including harmonic in this case here. And again, the reason that is true is because when you do the integral, x must be in the denominator in order to converge. So take a moment and copy that down, and hopefully looking at this example helped see why that's so. Pause the video, get caught up. This slide right here, can you please just pause and copy it? It's the next test. We're going to talk about it in class. I just want you to have all the stuff written down. See you soon.